In my previous videos, I had one video in which I talked about what algorithms are and why we study them. Then I had another video in which we talked about the growth rate of functions and asymptotic notation. Now we're ready to start analyzing algorithms. But instead of just jumping into analyzing full-blown algorithms, instead what I want to do is create some building blocks of understanding. So we're really just going to look at some code snippets, at least for the most part. That is small pieces of code so we can kind of understand what the process is. And once you understand that, that will make it easier to understand full-blown algorithms. Now what I'm going to use is code written in the C programming language. If you programmed in C++ or Java or C, of course C itself, or even something like Python, you should be able to easily follow along. Now sometimes when you look at analysis of algorithms, they'll use pseudocode, and that would be fine too, but I'm just going to use actual code. Now keep in mind that when you write a program in C, you have to compile the program. And ultimately we're trying to get an executable, somewhere over here. But there's something that happens along the way. So when you use a C compiler, it translates your C code into assembly language, for that particular computer architecture. That's why if I write a C program and compile it on my Linux computer, I can't take that executable and run it on a Mac computer. I would have to recompile it for the Mac. Now the assembly language ultimately gets then translated into some type of machine code for your particular computer. And the amount of clock cycles that it takes to do something can vary. So for example, if I wanted to add two integers together, this would probably cost many fewer clock cycles than if I were to perform division of floating point numbers. So 3.4 divided by 7.2. This right here probably takes much more effort than this would on your computer. So unless you're willing to go through and figure out what assembly language would be generated, and then how much effort your computer takes for each of those assembly language instructions, and look at the particular data you're processing, that would be a tremendous amount of effort on your part. In fact, much more than just writing the program and running it. So what we're going to do is make the assumption that each instruction or each statement, actually, for what we see, statement, has a cost of 1. Okay, that will make it easier to analyze. In terms of how long it truly takes to run your program, in terms of an exact number, this obviously wouldn't give it to us. But it is good enough to let us compare different things and say, well, this algorithm, say for example, appears to have a growth rate of n squared, say in the worst case. Remember, this doesn't mean worst case, but we can have big O for worst case or average or best case or whatever. So we might say one algorithm has a big O value of n squared, while the other has, big O value of log base 2 of n. And since this is much less than this, as n gets bigger, this might be your choice. Okay? So those are the assumptions we're going to go with. So now let's start looking at some things. Here's a simple for loop. Now, you may write the code and never really think about what it does, but let's draw a flow chart to show what really is happening here. So a for loop in C has these 3 parts. There's one part, semicolon, second part, semicolon, third part. The semicolons are required, but each of the 3 parts could technically be left out. But nonetheless, for what I have here, the flow chart looks like this. We probably have some code above this. In fact, we would have to declare the variables. But here we're going to initialize I to 0, and then we immediately come over and ask the question, is I less than n? And it's possible that the answer is no, it's possible that I is not less than n, and the loop fails immediately. If n was already 0, this will fail, and therefore we never update the sum. Okay? But assuming it is true that I is less than n, Then we'll add I to the current value of sum and update. So sum plus equal I. Then, because we're at the bottom of the loop here, if you need it, I'll put some curly brackets here, but they're optional in this case. Once we're at the bottom of the block, then we go up here and initialize, or excuse me, increment I by 1. And then we go back up and ask, is I still less than n? If the answer is yes, we enter back into the body again, then we increment I, come back up, and keep doing that until eventually this is a false statement. And when that happens, we come down here and then presumably do something else. All right? So I think it's easier to analyze if we assume a certain value of n. So let's say let n equals 3. And then ultimately we will need to turn what we do into a function of n. But this will make it easier to understand and also make the loop eventually stop. So what happens? Well, I is equal to 0. And then we'll ask, is 0 less than 3? Because n was 3 in this case. The answer is yes. So I'm going to update the sum. Then we'll do I plus plus. I will now be 1. Then we ask, is 1 less than 3? Right? We don't come up here and do I equals 0 again. That only happens once. Is 1 less than 3? Yes. Update the sum. Increment I to 2. Is 2 less than 3? Yes. Update the sum. Increment I to 3. Is 3 less than 3? The answer is no. The test fails and we leave the loop. So what kind of statements do we have here? Well, I have I is equal to 0. I have is I less than n. I have sum plus equal I. And they have I plus plus. Right? Everything here is one of these 4 things. So how many times did we see I equals 0? Well, that happened 1 time. What about I less than n? There's 1, there's 2, there's 3, there's 4. Sum plus equal I, 1, 2, 3. And I plus plus, 1, 2, 3. Now this would show a cost of 11 instructions. If I add that correctly, that's 5 and 8, or 5 and 6, excuse me, it's 11. But we need a function in terms of n. So we need to think, how do these relate to our value of n? Well, remember we said I equals 0 happens once no matter what n is. So if n is 1,000 or 1,000,000 or whatever, it won't matter. This will still just be 1. But I less than n happened 4 times. Well, n was 3. This happens to be 1 more than that, but is that a coincidence? Well, no. Let's think about it. This particular loop runs n times. But it has to ask the question, I less than n, 1 additional time in order for it to fail. Which is why when n was 3, we get this is equal to 4. What about sum equal, or sum plus equal I? Well, the loop runs n times, so this executes n times. And likewise, I plus plus happens n times. So now we have a cost of what do we have here? 1n, 2n's, 3n's, 3n plus 2 as a function of n. So when n was 3, we have 3 times 3 is 9 plus 2 is equal to 11. So that is our cost here in terms of n. So what are our values, big O, big theta, whatever? Well, can we bound this above by a function of n? Yes. Now, we could bound it above by n squared, n cubed, n to the 15th power. We could do all that, but remember we want this to be tight. If I were to multiply n by, say, 4, because remember we're looking for something like this, c of g of n, if you saw my previous videos. 4n is greater than or equal to this after some point. Maybe not initially, but once we reach a certain point, it would be above this and always stay above this. So we can bound this above by some multiple of n, so we say it's this right here. What about bounding it below? Well, 3n is less than or equal to this, obviously. So that's also a function of n. And because these two are both functions of n, if this was n squared and this was n, we wouldn't be able to do this. But because this is n and this is also n, we can say this is big theta of n, which is a better, remember this is tighter than either of these individually. So if we can say this, that's actually a little bit better. How do we know that this is really the correct amount? Well, we can look at the limit. So the limit as n approaches infinity of n over our cost function, 3n plus 2, is equal to the limit as n approaches infinity. Divide this by n, divide this by n, I get 1 over 3 plus 2 over n, which is equal to 1/3. So how does that help us? If the denominator function had grown at a much, much faster rate than the numerator, this ratio would have headed towards 0. And this is not equal to 0. If the numerator had grown much, much faster than the denominator, for example, if I use n squared, we would have gotten infinity as the limit, which is also not true. So because this is a positive, non-zero, well, I mean, technically 0 is not positive, because this is a positive constant, that tells me I found the right order of growth. That's what we're talking about here, order of growth or rate of growth of this cost function, right? So that's something simple. Let's do something a little more complicated. Let's assume in this case we already have an array A and it has n elements. And what we want to do is go through the elements of A and ask for each of those, is the current value less than 4? And if it is, we update a count. Now I'm not going to show you the flow chart. We'll assume you can follow that at this point. But let's assume again n is 3 so we can actually see what's happening. And let's work our way through this. So once again, I have I is equal to 0 initially. Immediately come over here and ask, is 0 less than n? If so, I'm going to ask this question, is a sub I less than 4? And if the answer is true, we update the count. But if it's false, we don't update the count. So I'm going to put maybe on this. Then we do I plus plus. Then we go up now and ask, is 1 less than n? Is a sub I less than 4? If so, update the count. So that's a maybe. Do I plus plus. Now it's 2 less than n. A sub I less than 4. Update the count if so. So that's a maybe. I plus plus. Is 3 less than n, or 3 in this case. These are 3's. And finally, it's a false statement, so the loop ends. All right? So there's the values we have to work with. Let's do what we did before in terms of the costs. So we had I equals 0, which had a cost of 1. We had is I less than n. That happened 1 time, 2 times, 3 times, 4 times, just like before. How many times do we ask is a sub I less than 4? 1, 2, 3. How many times do we update the count? Okay, that was somewhere. If it was never a true statement, it happened 0 times. But if it was always true, it happened 3 times. So 0 to 3. And then finally, we incremented 3 times. Now, what are those in terms of n? Well, remember, once again, I equals 0 only happens once. 4 was n plus 1. 3 was n. Let's jump down to I plus plus. That's also a good n. And what do we have here? Well, it could happen 0 times, or, this is not minus, this is 0 to 3, or it could happen as many as n times. Okay? So if we look at the min cost, which is when a sub I less than 4 is always false, so we never update the count, what we'd have was 1 n, 2 n's, 3 n's, plus 2, just like we did before. And the max cost would be that this statement right here was always true, What's that? N for n plus 2. Okay, so both of these are functions of n, right? There's no substantial difference between the two. So we get, this is big O of n, big omega of n, and because this is n and this is also n, so if this had been n squared and n squared, we could do the same type of thing, but since they're both the same function, that's big theta of n. Let's do another. Now let's nest some loops. So what I'm going to call the I loop runs n times, right? Because we're incrementing by I. The K loop inside runs n times. And on each iteration of the K loop, we update the count. Now because we have two loops, now I'm just going to say let n equal 2, because otherwise it's going to grow too much on us. So once again, we'll have I is equal to 0. We ask, is 0 less than 2? And if it's true, what do? We enter the inner body of the loop, right? We start doing the K part, where we'll say K is equal to 0. Ask is 0 less than 2. So let's put here, this is I, this is K. If that's true, and it is, we're going to update the count. Then we increment K, right? Then we come up and ask again. Now is 1 less than 2? That's still for K. It is, so we update the count. K plus plus. Is 2 less than 2 for K? The answer is false. So now we're at the bottom of the loop. We return to the loop this is embedded in, which is the I loop. We're at the bottom of it, so we increment I by 1. So we have I plus plus, and then we repeat. So now we're going to come over here, and now we ask, is 1 less than 2? But this is for I. And now I'm going to repeat this portion here, and then we'll do I plus plus, which will make it 2, and then we'll get that 2 is not equal, or excuse me, not greater than 2, and it fails. Right, so this code right here would just go here again. Right? So what are the costs here? Let's look at the K loop first, the part that's here and here. So K costs will be K is 0, K is less than n, count, plus plus, and then K plus plus. So this happens once. How many times does this happen? N was 2, but we said 1, 2, 3, 3 times. We asked if K was less than n. This happened twice, count, and then K plus plus happens 2. And in terms of n, this is still just 1, n plus 1, n, and n. And the cost on this is 3n plus 2. Just like we had before, right? That's just for each of these K loops. So that happened here, that happened here. What about I costs? I is equal to 0. Is I less than n? If so, then we have the K loop. I'm going to write it like this, K loop. And then I plus plus. So what happened here? This happened once. This also happened 0 less than 2, 1 less than 2, 2 less than 2. Sorry, I can't quite see that. So it was 3 times. So that's 1. That's n plus 1. How many times did we run the K loop? Well, it was n times. We saw it 2 times here, which is n times something. We'll call it K cost. And this was also 2, which is n. So now what do we have for the total costs? Well, for the I part here, we have, let's look at this and this. So I have n here, so I have 2n plus 1 and 1 is 2. Plus then I had n times the k-cost, 3n plus 2. So that's still 2n plus 2 plus 3n squared plus 2n. We write like this, 3n squared plus 4n plus 2. So that should be the cost for this. So now what is the order of growth? Well, think about what grows the most. If you watched my video where we looked at different functions, log of n squared, factorials, whatever, which part of this seems to grow the most? Well, 2 is always 2. If n was small, these aren't that different, but let's say n was 10. Well, this is 4 times 10 is 40, but this would be 3 times 10 squared, which would be 300. So this is the part that's really taking off. And I look at this and see the n squared. And so I'm going to get that this is big O of n squared, big omega of n squared, and therefore theta of n squared. Is that right for this? Well, let's look at my limits again. Limit of n squared, as n approaches infinity, sorry, of 3n squared plus 4n plus 2. And if you work all this out, you'll see this is 1/3, right? Because we divide the top part by n squared, the denominator by n squared would give me 1 here, give me a 3 here, plus terms that are being divided by some multiple or some power of n. And you get this, so that is correct. So you'll see this, and the reason these are all focusing on loops is because, once again, for lots of things that you're repeating a process, that's where the cost comes in. You just have to figure out what it is. Now, you may be tempted to look at this and say, okay, well, this was n, this is n, so it's just n squared, and that was true here. But occasionally you'll see an algorithm where the way the internal part works is such that you can come up with a tighter bound than just to say n squared. Let's look at something slightly different now. And this would actually be closer to a real algorithm. So let's say we have what in C terms will be an array. Something looks like this. 13, 4, minus 5, 62. But in more general terms, you might say a list. Now, let's say we want to search the list for value, and let's assume the following. Value is in list, so it will always be here somewhere. And 2, don't know order of elements. Which means this could be sorted, it may not be sorted, it may be reverse sorted. We don't know, so we're not making assumptions. And when that's true, typically what we would do is perform what's called a linear search or a sequential search. So basically it's this. If I'm looking for the number -5, I come here and say, is 13 -5? No. So I come over here, is 4 -5? No. Is -5 -5? Yes. So I stop. So I just start on one end and start working my way through. Okay? So our algorithm would look like this in C terms. Int search. We'll say it's int array A, capital A that is. Int n, because there's n elements in it, and int value, the thing we're searching for. Int I, for I equals 0, I less than n, I plus plus. If a sub I equals value, then we return the index, which is I, of where it's at, and then you could retrieve it or whatever you're trying to do. And then we close this up. Okay? So if we did not know that had to be here. If the first assumption was not necessarily true, then this could lead to a problem. Okay, we might want to have another return statement that told us something, but that's what we have here. Now let's remind ourselves that big O does not mean worst case. Instead, big O is an upper bound on the rate of growth of the function. Okay? So let's look at some scenarios we have here. So what is our best case scenario? So we could have a big O for this, best case, a big O for worst case, a big O for average, whatever. What would be the best case for this? Well, the value is in the first place we look at, right? If we start looking at the leftmost element, which in C terms would be A sub 0, if we start here and we find it, we're done. We don't need to go there. Even if there's a billion values here, we stop immediately. So that's our best case. So value in first place searched, we'll say. So what's the cost of that? Well, it turns out that right here has a big O value of 1. Okay, is what we call it. And there's also a lower bound on that of 1, and therefore we can say this. What about worst case? Last place we look. Right? If there's 1,000 elements, the worst case for us is we have to look at all 1,000 to finally find it. Or technically, if we know it's there and we look at 999 of the 1,000, don't find it, we know it has to be in the last. But basically it's big O of n. And ultimately what we would see, it's big theta of n. Okay? So those are relatively easy. But what about in general? That is what we're going to say is the average case. Okay? Okay. So now we have to really do some actual analysis. So let's think about what happens. Let's use this sample where we have 4 positions again. And I don't remember the numbers. We'll say it's 3, 9, 5, 14. So what are our possibilities here? So let's say the value in the first place we look, A sub 0, how many comparisons did we have to perform? That is, how many times did we say if A sub I equal value, that's our comparison. How many times did we say that if the value we're looking for is 3? Well, just 1. So number of comparisons. That's what this column is. And if the number we're searching for is 9, then we had 2 comparisons. Or sorry, this would be 3. 3 if we were looking for 5 in this case, and 4 if we were looking for 14 in this case. And therefore what we get ultimately is that the last position, which in C, since indices start at 0, this would be n minus 1, but it would take n comparisons, right, to find the value you're looking for. So on average, what is the value? So one way to look at that would be this. And we're assuming these are equal odds. So assume equal probabilities. And value in list. Again, we're sticking with that. Okay. So to find the average, so say there's 10 things, and it means 10% of the time it would be this, 10% of the time it would cost you 2, 10% of the time is this, and so forth. So we have 1 plus 2 plus 3 plus ... plus n over n. And what is that? Well, the top part, there's a formula for this that says that 1 plus 2 plus 3 plus ... plus n is equal to n times n plus 1 over 2. That's the formula. So this right here then will be, take this right here and divide by n, which gives us average n times n plus 1 over 2 divided by n, which means multiplying by 1 over n. That cancels, that cancels. We have n plus 1 over 2, and this becomes average is equal 1/2 of n plus 1/2. Okay? So what's the order of growth on that? Our big O on this then will be our n. Okay? Remember, worst case was n, so it can't be bigger than that. But basically what it's telling us is that if there were 10 things here, it would take approximately 5 searches, right? It would really be, in this case, 5.5. But it's approximately 5 searches on average to search 10 things given certain assumptions. There's no particular order. We assume there's equal probability of values. The value is in the list, that kind of thing. Okay? And this also would lead to this. Before we move on, though, and look at this in a slightly different way, let's think about this different. This is a fine way to calculate this, but let's think of it differently. What if we take this right here, then we have our average is equal to 1 over n plus 2 over n plus 3 over n plus dot 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 plus n over n, right? And we can think of that as 1 over n times 1 plus 1 over n times 2 plus dot 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 1 over n times n. If there's, say n was 10, if there's 10 positions and they have equal probability, then there's a 1/10 chance, 1 over n, 1 over 10, that it's here, or that's here, or here. So what we're doing is taking basically the probabilities of each particular cost being what we get. So 10% of 1 plus 10% of 2 plus 10% of 3 and so forth is what this is. Thinking about it that way will help us in our next situation. But thinking about it this way is also perfectly fine. Let's look at this problem differently though now. Let's change something. So now let's say we want to search an array of ordered values, or sorted. Let's say sorted maybe. They're somehow sorted, okay? So we know, for example, if these were our 4 values, we might have 3, 5, 19, 24. We're going from smallest to largest. So we're still going to assume value in set or in list and equal probabilities that the values we want is any particular place, right? But now we can take advantage of the fact it's ordered and perform what's called a binary search. When you look at words in a dictionary, you just don't pick positions at random, right? Like, for example, if I have an American English dictionary, which is what I would use, I go from A to Z, and if I'm looking for a word that starts with T, I'm going to look somewhere down here. I don't just start at the beginning and start working my way through all the words. Now, I can take advantage of the fact that I have some idea of the distributions of letters, right, in terms of how they start words. There's more words that start with A than start with Q, for example. But I can still take advantage of certain things, and if I look for a word that starts with T and actually get S for where I open the book, I know that T has to be on this side. I know go this direction. So with the binary search, what you do, and I'm going to use numbers that tell us where we're at, actually. Let's say that I'm looking for the number 6. Search for 6. So what I'm going to do is I'm going to look at the midpoint. And so the middle number is 4. Because I know this is ordered, I know that 6, if it's in the list, and we're assuming that here, I know it has to be to the right. In fact, let's say we're looking for 5, because that will let me do this longer. Okay? So I know 5 has to be to the right. So what do I do now? Now I find the midpoint of this half. And now, because I get 6, so I got 4 the first time, I got 6, I know since 5 is less than 6, it has to be on this side. So I slowly keep weeding out half of what I'm currently looking at. And so a way to represent this would be to use what's called a binary tree. We can think of this as being structured like this. 4, half of this side would be 2, half of this is 6, 1, 3, 5, and 7. And so this tree here has what's called the binary search property. Everything to the left will be less than or equal. Everything to the right is greater. So all 3 of these are less than or equal to 4. We look at 2. 1 is less than or equal to 2, but 3 is greater than 2. 6 is greater than 4. 5 is less than or equal to 6. 7 is greater than 6. So we always know which side to search. So if I'm once again looking for 5, I say, well, 5 is greater than 4, come to here. 6 is not equal to 5, but it has to be less than or equal to that, so we come here. And if these had children, we'd keep working our way down. Okay? So how do we analyze this? So what's our best case here? Just like before, value in first place we search. In the example I just showed you here, if we're looking for 4, 4 would be the value. I mean, it would be we would find it the first time and we stop. Okay, so in this case, we have big O or theta in this case of 1. But what is worst case? Let's think about we have a tree that looks like this. The actual values don't matter for this analysis. And I'm drawing the tree to have every row or level full. So what's worst case here? It's not here, so I go one way or the other. So let's say I come to here. It's not here, so maybe then I look here. It's not here, so I come here. Worst case is I go all the way to the bottom. So the question then is, what is that? What is the cost? Here I happen to have 15 nodes in this example, but it didn't take us 15 comparisons. It took us 4 comparisons, right? So let's look at some analysis. So we'll write these as the level. So this will be level 1, level 2, level 3, level 4, or the height. We'll say these are the height. Okay? And how many nodes? Each of these circles is called a node. We're involved in this. Because this is relevant to how we construct a tree. Because we're never going to have something, in this case, we're never going to have something, if we have this set up, if we think about it as a binary search tree, not just a binary tree, but binary search tree, if we think of this as like this, it's never going to be like this, where it's sort of lopsided. We're sort of balancing it out. That's the reason why we have speed. So if we look at number of nodes, if we only had one level, we just have one node. 2 levels, 1, 2, 3. 3 levels, we have another 4, so it's 7. 4 levels, we add another 8, so it's 15. If I look, that's 2 to the first minus 1. That's 2 squared minus 1. That's 2 cubed minus 1. That's 2 to the fourth minus 1. So the number of nodes, so if my level goes down to h, this value here will be 2 to the h minus 1. Okay? So what we really want to know, like if we had to go all the way down to here, we had 4 searches or 4 comparisons, we need to be able to get the 4, which happens to be the h. So what do? We're going to use logarithms. Okay? Now it turns out if I were to take the log of this, log base 2 of h, I get 0. Log base 2 of 3 is 2.81. Log base 2 of 7, excuse me. Or sorry, this should be 1.51. Or 8, sorry. I'm looking wrong. I'm copying this off a piece of paper. 2.81. 3.91. Well, these values obviously aren't exactly 1, 2, 3, 4. How do we get those? Well, what we can do is we can use a floor function. Okay, so we say the floor of log base 2 of n, okay, because this was 15, log base 2 of 15, so this actually, sorry, is n, plus 1. So what happens there? Well, if I had 0, right, I only had one node, log base 2 of 1 gives me 0. 0 plus 1 gives me 1. If log of 3 gives me 1.58, I add 1 to that to get 2.58. I round this down to the largest integer less than or equal to this. That would give me 2. And so forth for each of these. So each of these then will give me 1, 2, 3, 4, and so forth. Okay? So this right here, this ultimately allows us to get the value. So what is that in terms of big O? What's the logarithm that matters? So you'll see it often written like this. Remember, this right here is log base 2. That's the big O value for worst case. All right. So what is average? Turns out average is somewhat difficult to come up with a formula for. So I took this formula from Wikipedia, which in turn took it from the book by Knuth. You can look at that if you want to try to understand how he came up with it, or he doesn't get really quite explain it. Knuth, The Art of Computer Programming. Volume 3, which is the one on searching, and it happens to be in section 6.2.1. So the number of comparisons as a function of n, so I'm going to say f of n, is equal to this. The floor of log base 2 of n plus 1 minus this fraction. This would be 2 to this power, the floor of log base 2, and then add 1 to that, subtract the floor of log base 2, or excuse me, this is log base 2 of n, this should be n, this also should be n, sorry, minus 2, and that is approximately equal to log of n minus 1. That is, you take the log base 2 of n and subtract 1 from it. Okay? And so from this you get that on average, for the average case, is big O of log of n again. Now I can't claim to understand where this function came from, but I can show you how I calculate the costs. So let's say we have this again. I'm going to do it with full trees. So here we happen to have n equals 15. So if we assume each of the 15 positions has equal probability, if the value is at the top, we have to only make one comparison. If the value is at the second row, we obviously have to make two comparisons, one here and then one for one of these. And the third row requires three comparisons, and the fourth row for the fourth. But what are the costs? Well, each of these 15 positions has equal likelihood. So the probability that this is my number is 1 out of 15, this is 1 out of 15, this is 1 out of 15, 1 out of 15, 1 out of 15, and so forth. So my average here, and this goes back to what I told you earlier about a way to think about it, is how many values, what's the probability that I only have to search once? It's 1 out of 15. What's the probability I search twice? Well, there's two different values here now, so it's 2 out of 15 at a cost of 2. What's the probability that I make 3 comparisons? Well, there's 4 of these, so that's 4 15ths. And then finally, there's 8 out of 15 in which the cost will be 4. And this right here is equal to 49 15ths, which is approximately, really, let's say approximately 3.2667. If you use this function here, we get f of 15 is also approximately equal to 3.2667. So I got the same value both ways. All right. What if we had a tree that wasn't complete? Let's say we had this, but it's still balanced as much as we can. So here we have n equals 10. Okay, so the fourth row just has these 3. The function tells me this right here is equal to 2.9 exactly. And my method, once again, now it says there's 1 out of 10 values have a cost of 1. 2 out of 10 have a cost of 2. 4 out of 10 have a cost of 3. And 3 out of 10 on the last row have a cost of 4. So there's 3/10, which is 29 over 10, which is 2.9. Same thing as here. Right? We said that this right here was approximately this. Is that really true? Well, I ran some values, and so we'll say I tried n was equal to 7, 31, 1023, and also tried 2 to the 20th minus 1. Let's draw some lines here. So using the formula, or my method, I get 2.4286 for 7. For 31, I got 4.1613. For 1023, I got 9.0098. And to 4 decimal places, for the last one, I got 19.0000. On my own, when I extended the number of decimal places, I saw it wasn't necessarily exactly 19, but this is what I had here. So what if we use our approximation and try log of n minus 1? Well, for small numbers, it's not that close. 1.8074 for 31. I got 3.9542. This one I get 8.9986 as opposed to 9.0098, so it's pretty close. And this one, to 2 decimal places, I also got this. But once again, when I extended it to 7 or 8 decimal places, these numbers weren't exactly the same. But you can see in the extreme, as n gets bigger and bigger, this approximation is pretty good, which is why we can use this for our big O amount. Okay? So there's basic analysis. What I will do in my future videos is I will take actual algorithms for sorting and show how to come up with big O values for those.